Hey everyone, what's up? Oh my goodness, science, and a lot of science today. I think I had a better intro for this stream in my head, and then I forgot it because I didn't write it down. Huh. Well, I think my intro was something along the lines of the fact that, yes, in fact, I did have a lot of science in the form of, last time it was in the form of watching a all-day seminar at work on, vacuum pumps and other stuff like that, vacuum systems. Today, and actually this whole week, is because I was actually attending the American Chemical Society 2026 150th year anniversary virtual conference for the last couple of days. So I've been listening to science people give presentations about, their chemistry work, what the cool stuff that they're doing is. And most of the time, they are delivering it through the quality of, like, a shitty, like, iPod microphone, as if such a thing exists, but you get the picture. It's, as I kind of ranted on Tuesday, it's still astounding to me that after the pandemic, we still have people who just refuse to understand the fact that it sounds like they are speaking through a drive-through window. And can't afford even, like, a $30 microphone, and, like, if can't afford a $30 microphone when they are a professor, tenured professor, who probably makes, like, $200,000 a year, and also, God forbid, they actually know how to use Zoom or operate PowerPoint. I don't get it, because these are the absolute things that would probably get us, like, get students, like former me, ridiculed for, if they were trying to do, like, a presentation to the group or to, like, for their candidacy exam or something. Yet, professors, of course, being the ones in power, have the upper hand to just be like, it's okay, I don't have to know how this technology stuff works. Y'all will figure it out for me, and then proceed to wonder why no one's listening to them at presentations anymore.
Why do they sound like this and they can't even be made out properly?
Fucking anyway, stupid, dumb, long gripe, but I don't know, the conference was, I mean, I'll hesitate to say it's fun. I mean, it was, in fact, listening to lots of science, which I like chemistry, of course, so I think it's cool, but fun? I don't know, it's still kind of work. But, I did get to hear some, like, neat, little advances in, like, PFAS, chemistry, perfluoroalkylated substances, the hot new thing that RFK Jr. is making sure we actually have a healthy dose of in the water instead of, I don't know, removing it like any sane person would do. And what other stuff? Like, there's a little thingy on, like, psychological safety, which is basically, like, make sure that your work environment and work culture is not one that yells at people for making small mistakes, and people could actually grow in an environment where they are allowed to make mistakes and receive constructive criticism. This is a thing that needs to be told to people. But genuinely, it was a really good seminar. Like, the presenters were great, so I had a good time with that. Anyways, I think that's enough plotting and waiting for people to, pile on in. People have gotten 8 minutes to get into the stream, so I think we can get going with things. On over to the other layout. There we go. Hey, it's me. And look at that. That's the music that I used for today's stream. Kirby Superstar taking over the Halberd, X-Style Remix V2 by Mega SFC. Great Mega Man sound font remixer, and occasionally Kirby sound font remixer too. If you have not watched or subscribed to Mega SFC yet, please do. Small channel, they're great. Like, they're fantastic. They're one of the best in the biz at what they do. But anyhow, we can move off the music then here. We can get on over to today's science. I guess I'll explain today's science before taking off the audio. So today we're going to be starting off with actually the reverse order of the title. I want to, instead of doing glass, gas, and ass, I want to actually start off with ass, as many content creators want to do, and then move into glass and then gas, because I think gas is the most interesting one, and I want to watch that at the end. This one is probably still going to be interesting, but a bit drier. So I'm happy to start off with it first, just so that way, not the demographics, the population stream tends to increase as the time goes on. So it'll be saving the best for last, as it were. All right, hey Scorpor, ass indeed, ass ahoy. Whoa, ass ahoy. Where's Brian Griffin when you need him? Someone please pull me off of stage right now. Revoke my comedy license. I'm pretty sure I deserve it for making that joke. Alright, anyways. On to Retracted Arsenic Life from Periodic Videos. I think...
15 years.
Oh, well, here we go. I tested the audio a little bit before stream started, so I kind of got spoiled on the topic. This is going to be a discussion of how a handful of years ago, 15 years ago, as the professor says here, there's some publications on life living in a very polluted waterway in California. The waterway was polluted with lots of arsenic. Arsenic is in the same atomic group as phosphorus, and so theoretically could maybe be incorporated into the life's, biomolecules like ATP and stuff like that. Maybe some proteins. But it seems that this paper has been retracted for not having the best science, not drawing the best conclusions. So let's get the full story here.
Ago, when I talked much faster and looked much younger, I was very excited about a paper that had been published about bacteria that lived in a lake in California where there was a lot of arsenic in the water. If there isn't any phosphorus, then you could use arsenic. And the authors of the paper claimed that the bacteria could make DNA from the arsenic in the water rather than from phosphorus, which is normally found in DNA. Even when the paper was published, there was quite a lot of controversy and argument. Was it right? How can this be?
I'll say that is for any kind of biological related paper, and with good reason too. If you suggest that, an element can be replaced with its cousin that's right below it, which should have similar electronic properties at first glance, that is one of the ultimate things in science culture that is going to rock the boat, because life is only arranged in one way as we know it to be healthy. And replacing even, there are certain metal centers or what are called cofactors within certain proteins within animals and plants. And replacing the metal center with a very nearby cousin, that's very controversial because you don't see it very much. And it can have wildly different effects on the molecule, and usually it does. Usually it doesn't work, but there's the occasional time where, for example, there's a I'm not remembering it very well, but there is a cofactor that's useful in, I think, hydrogen generation in certain bacteria, and it uses a molybdenum core as its a workhorse. And the heavier cousin tungsten also has a hydrogen cofactor in certain other species of bacteria that does the same thing. This is exception to the rule. And so to assert that you can replace phosphorus with arsenic, not only arsenic being itself toxic in its pure form and its ionic form, but also the fact that arsenic's a lot larger than phosphorus and certainly has, for complicated reasons I can't quite get into here, a less aggressive pair of electrons to attack and bond into other molecules with. This is a bold claim and a half.
Arsenic is poisonous, and so on.
My name is Dwayne Brown with the Office of Communications. So, we end a week of fiction. Today, we begin the day of facts.
And our video, although I was very enthusiastic, did have a few so-called weasel words saying they may have proved this, but we're not sure. Or appears
Never
to
heard
show,
that term
because
before.
there's
Must
still
be a
some people
Britishism.
have slight doubt. So what appears to have happened in this case, what this experiment seems to show, now, they haven't proved, for example, life could adapt. Now, there has been a very interesting development in that the editor, or the present editor of the journal, one of the most famous journals in the world, scientific journals with the name of Science,
Oh,
the
yeah, that's a
editor
big
has
name.
decided that.
So for reference, for those of us not in the publishing world, the journal Science is quite possibly the or second, either the most or second most prestigious journal you can have your work published in. And it's basically that prestigious because it basically means that your work is so potentially influential that people in other fields need to hear about this, because nature and science are both general like general broad like STEM science research journals. You'll have stuff in there you'll have stuff published in Nature and Science that are biology, that are physics, that are chemistry, as opposed to a lot of other journals where you're going to publish your chemistry work in a chemistry focused journal. So if you're getting into Nature and Science, that means that your work has implications, or at least has potential implications for other fields. Something like this that's like, wow, bacteria may be using arsenic. That is impressive even without a too much of a biology background, and could potentially reshape how biochemists might think of things, rather than, and maybe how chemists think of phosphorus and arsenic, for example. So yeah, to get into science is big. To get retracted from science is a pretty bad stain on your reputation, possibly, or a bad stain on the journal's reputation. But we don't care about the journal that much. They charge you to publish your work.
Name of Science, the editor has decided that the paper should be retracted, that is, taken back, and not accepted by the journal. Now, from time to time, papers are retracted, but they're usually retracted because somebody has been found to do some sort of fraud, or perhaps what is becoming more common now is using some sort of program like Photoshop to change images to make them
data manipulation
look better and to prove
another thing that AI
prove a
worsens.
scientific point. In this case, is slightly different. The editor has said that the paper does not prove the point. Not that there are any mistakes, but the experiments that were done didn't really show what they were claiming to show. And this is new territory. And the authors, well, one of them has died, but the remaining authors are really quite angry. They have written a reply.
All right, so nearly 15 years later, the editors of Science have retracted our publication. We do not support this retraction. Where it could have been written and discussed more carefully, we stand by the data as reported. These data were peer-reviewed, openly debated into literature, and stimulated productive research. We disagree with this standard, which extends beyond matters of research integrity. Disputes about the conclusions of papers, including how well they are supported by the available evidence, are a normal part of the process of science. Scientific understanding evolves through that process, often unexpectedly, sometimes over decades. Claims should be made, tested, challenged, and ultimately judged on the scientific merits by the scientific community itself. All right, I mean, obviously, the research group has incentives for wanting to stay published in science. I kind of just outlined them a second ago. It's a good journal to be published in. But, I partially see their point. Like, they want... The point they're trying to make here is that it would be better to have their publication with some evidence, maybe not completely conclusatory as evidence, still published, so that way other people in multiple fields and in their field could look at it and, say, hey, maybe this could be tested better. Maybe I could test this better. Maybe I could write a paper following up on it. Of course, I imagine this group probably followed up on this and maybe made some more papers out of it, but I'm going to go on the assumption that maybe they didn't, because otherwise I bet this one wouldn't be so controversial. But yeah, the argument is, I would say the group's argument's a little bit flimsy. I'm already, not to defend the $1 million corporation, but I mean, I am a kind of on the side of like, if your data doesn't show things that Verizon just won't repair. Oh, that's good. OBS reconnection successful. Give everybody a second to catch up. Go ahead and press the +5 to 10 seconds on your YouTube bar now. I'm sure you're not going to miss anything because I'm going to extend the sentence out for a little while. Okay, so I am on the side of maybe this is worth retracting because if your paper does not have enough evidence to push the conclusion you are trying to imply, then it's not that it's not worthy of publication and debate so that way someone else could take a look at it. It's that it's not worthy of the journal Science. It is more appropriate for what is known as like a communications or at least a lower journal that might still be, it's not that the lower journal's bad or that a communications is inherently bad science, not a reflective on like, your research being fruitless or terrible. It's just that small reconnection successful again. All right. Yeah, it's I'm gonna actually add that to my to-do list right now. Complain to Verizon this weekend. Because this is happening way too often and they are not fixing it on their own. Internet. Okay, there we go. All right. What the hell was I saying? I already forgot. Hold on. Fixing another thing on my phone. Okay, yeah. So it's something like this. I feel like if you don't have very strong evidence, would be better for a lower journal or communications, just so that way you can get the idea out there, stake your claim on the potential for the idea, but it doesn't necessarily say that you're like totally standing by the rock solid evidence behind it. I get the feeling it's just that the research group does not want their publication pulled out of one of the most prestigious journals in the world. Okay, going forward.
The rules have changed. You shouldn't do this. But it is clear that there's more doubt about the paper than we thought when we made our video 15 years ago.
I suspect we would all agree that we would have written the paper a little bit differently if we had to do it over. We would have been a little bit sharper about what the paper is absolutely claiming to be the case and what is a bit more speculative. The paper was a little bit fuzzy about that, and that allowed some of the public relations and media and some of the authors too in conversations to maybe drive things a little further than needed to be driven. So we don't think that. So obviously we don't think that there was any kind of misconduct, nor does science, and we don't think there was any basic flaw in the data. We think this is a debate really about interpretation, and debates about interpretation are, of course, part and parcel of the scientific process. And papers are wrong all the time. That's kind of how science.
It's just starting to sound like yours did not
If
go
you're going to
far
start
enough
retracting papers because they turn out to be incorrect, then you've got to retract the whole. You've got to police the whole literature.
Professor, what do you think, though, about this bigger picture of going back through the archive of thousands, hundreds of thousands, millions of papers?
Yeah, Professor, offer some
and
drama.
Looking at them a second time, a third time, and saying, hang on, does this really cut the mustard? This is an interesting development.
I think in some ways it is a good thing, because if papers are left on the record, then people can use those papers to argue a scientific point, say, look, the evidence shows this, and if the evidence is flawed, then it should be clearly indicated. The question perhaps
like people actually read these
should the
things.
paper be completely retracted,
at least the people making those kinds of
or
arguments.
should the paper be left there, but with, as it were, health warnings saying it's very unlikely that this is true? And I don't know the answer of that, but it's clearly a debate we need to have. And it's becoming more important because people are using computer searching, artificial intelligence to find papers which in the old days they mightn't have found. But if a paper was
just
published
be the science
in
people
Science,
who could actually.
everybody can find it.
It used to more just be the actual researchers who could look at these old papers, and so it's more of an issue now where it's just like, I mean, it's good the public has more access to these papers, but, you know, it does also mean that you have to be more careful about, I wonder what the reader can interpret and actually, do their own kind of proofreading and fact checking, because the wider that pool gets, the less, let's say, scrupulous your audience is.
I guess I want to get some idea of the toll that it took on the other authors. We know about the lead author, and she's told her story in the New York Times and what she went through. Has it been the same for all of you? Did she cop the
No,
brunt of it?
it definitely did not. I mean,
Personal
she
attacks,
and
geez,
Ron
yeah, that's a
Ormond
little
certainly
far.
bore the brunt of the backlash. I think it affected all of us in some ways, but not in the same way. I mean, the lead author. I mean, she was at the press conference.
As Mary can probably knows, and as many of my colleagues would agree with, I'm always interested in exceptions to the rule.
And for a whole bunch of reasons, bore the brunt of the backlash, as you're well aware. And Ron, it was his lab, and so that was he bore a lot of backlash. He's no longer with us, but I know he felt it pretty keenly.
Professor, have you ever had a paper
Unfortunately,
retracted or withdrawn or
that's not that
stricken
short.
from the record?
80 years, but still.
Fortunately, not. I would be terribly embarrassed if I had.
Really? Would you not think this is good? This is science. This is how it works. What I thought was right 20 years ago turns out I was wrong. I would have thought you would
I mean,
think
where
that
your
was...
mouth is, Professor.
No, I think if somebody took one of my papers and showed I'd misinterpreted it, that would be fine. I'd be quite pleased. And in our video about my former student, Steve Church, I explained how he found a mistake in my thesis and corrected it. But that's rather different from finding that I had deliberately made a mistake or deliberately changed something that I shouldn't have done. I did have one paper.
Sounds like the professor is maybe accusing this lab of a little bit of underhandedness, or just ill practice, maybe. At least that's the implication. He probably doesn't mean it, but if we're gonna do the React slop, dig into things and dig into words for drama, then ooh.
And I won't tell you which one, which had got to the stage of the galley proofs. So it was just about to be printed, and my professor read it and found serious mistakes. But we managed to correct those mistakes before it was published. Otherwise, I would have looked really stupid.
What do we do about our YouTube video?
Oh, well, I think the YouTube video is okay. You could put a comment in the description saying, watch our new video to see further developments. I should say that my colleague Mike...
papers can do the same thing. It's just the issue of people might actually be more able to, or be more interested in clicking on the next YouTube video, the next part in the saga, rather than read the next paper in the saga.
Says that
if there even is
one of the things that distinguishes these famous journals like Science or Nature is that they have far more retractions than many other journals, because so many people are desperate to be published in these journals.
That they
Good point.
They push the limits.
The journal's trying to keep its prestige high.
I don't know that they push the limits, but they're sometimes more hopeful about their results than they really should be.
Yeah, they're pushing the publisher's limits.
Just because something is published in Nature, it doesn't mean that it's wrong.
There's different styles of science. There's science that is very hypothesis driven. You start with an intellectual framework of how the world works or how the system works that you're interested in, and you test it. And you test it in a kind of incremental way.
Right,
and
that's a scientific method.
For the most part, what we might call normal science. I mean, it is a very common, it's a textbook way of doing science. But then there's another style of science, which we might call discovery-based science, right? Where you say, I want to know what's on the other side of that hill. I have no idea what's on the other side of that hill. I have speculation, right? I may form a hypothesis to try to, because I want to be sure that when I go to the side of the hill, I don't get hurt, right? So I'm
Can't know
going
the
to form some kind
unknowns.
of idea that's going to guide how to do that. But I don't really know, and whatever I find there is interesting, and I'm going to tell people about it. This kind of discovery science. And then when you go across the other side of that hill, or for example, take the first images of the surface of Pluto, let's say, right, and you see things that you don't expect to see, then it's incumbent on you to try to explain what you see. And in that mode of science, we tend to welcome crazy hypotheses because you see something you didn't expect, right? And then you embrace you want to embrace or let into the room the full spectrum of ideas, because something that seemed crazy may turn out to be the right interpretation.
But a crazy hypothesis does not a nature paper make, does not a science paper make. It's good to mention the possibility. It's good to provide results that could support that possibility. But if your data don't conclusively show that possibility, then a lower journal publication that does make.
So in that first mode of science, you tend to be pretty constrained in what hypothesis you'll accept, because a crazy hypothesis goes too far beyond the intellectual framework you already got. In discovery modes of science, you tend to be kind of welcoming and even celebrating the crazy hypothesis that turns out to be right. So NASA in particular, we haven't mentioned NASA, right? NASA's in the business of discovery-based science very much, right? And so as you're probably aware, the NASA Associate Administrator for Science, issued a statement, opposing the retraction, because NASA feels somewhat threatened by this. If we're going to start retracting papers because a hypothesis that was put forward to explain interesting new data turns out to be incorrect, if that's grounds for retraction, then how do you do discovery-based science?
Thanks to Jane Street for sponsoring this video. Jane.
Interesting NASA has that. I mean, obviously NASA seemed to have some kind of stake in it because it seemed like one of the co-authors was one of their own, but I don't know. The idea that it's like, oh, well, this could be a massive threat to the, massive threat to the health of like the science journal ecosystem and ensuring that crazy hypotheses can still be made. That I don't know. To me, that feels like a big stretch. That feels like, as Professor Polyakov said in the interview with Brady back there, papers get retracted from Nature and Science quite often, and it's usually because the journals are really trying to keep their reputations clean and up and strict. And again, there are many other journals that are still good. They just don't have the insane prestige. It's not like you can't make a big claim. It's just that your big claim pretty much has to be right if you want to get into the, most prestigious journals possible. To actually have that prestige, you need to earn it. It's not like these people are bad researchers. They know a hell of a lot more about biology and the potential for arsenic life than I do, I'm sure. But, a lower journal they maybe should have shot for. Just saying. My chemistry-ass non-biology opinion. All right. Okay, so that's arsenic life. Next, we've already tore through the ass. Now we need to go over to the glass. I'm a little curious about this one, in the sense of, what do you mean turning glass to gold? So, I guess I can do some music for an explainer time here for a second. Yeah, that's in my stream playlist. I'll put that on. Good volume level. Okay. Alright, so, I was going to talk about is the fact that, refresh this to maybe get the thumbnail up, potentially. Alright, cool. So, oops, not the right thing I wanted to do. What was that? Okay, so I believe I've explained this before on the stream, but I want to do my due diligence and explain it again for any newcomers. So, common glass, like you have in your windows, is a form of silicon dioxide, which is, in other forms is sand. And it's these big silicon dioxide networks, where each silicon has 4 oxygens bonded to it. the oxygens themselves are, they were completely balanced, they'd be bound to 2 other silicons, and they can form just this large network that is importantly a amorphous and not very ordered network of oxygens and other silicons. So they're not going to be constrained to a plane. They're going to be kind of just wild and wobbly all over the place. And so as a result, you're going to have a structure that is amorphous and is not going to absorb light very well, so it's transparent, as we know glass to be. Yeah, so I think that's all we really need to go into. Just this is the general idea of what glass is. There's also usually like maybe some sodium positive ions in there to counteract when, or to allow for and counteract negative charges of oxygens binding to multiple different silicons. More than 2, 3 or more. Usually just 3. So the problem you might be able to figure this one out. Where's the gold in all this? I have no idea what this amateur chemistry person is talking about, unless he's finding like a very specific, like, you know, once in the 1960s there was actually this thing called hourglass, and it has the AU in the name because there's gold laced inside of it. Now you too can feel like a rich man when you're drinking your scotch at home. Like, unless that is the case of what's happening, I have no idea where this man is getting gold from in the glass. There's gotta be glass. It's gotta be special glass. That's the only thing I could possibly think of. But I also can't think of any special glass that actually has gold in it. I can think of special glass that has uranium in it, but I can't think of special glass that has gold in it. So, like, I'm very interested to see just what kind of artifact he's gonna pull out of nowhere. So, let's get to it then.
This video is brought to you by The Last Book.
Things
Hi
exploding
guys,
and burning.
welcome to Amateur Chemistry. So, I am sure we all know lead. This
Yeah.
soft and shiny metal
Heavy.
is famous for its high
Poisonous.
density and low melting point, making it an attractive material for things like plumbing, bullets or fishing weights. It also has many cool chemical properties, and throughout history, alchemists really liked to
there.
tinker with it, trying to make it into all kinds of things, mainly gold. Lead always kind of fascinated me, since despite being so useful and abundant, it just so happens to be one of the worst neurotoxins, literally making you dumber on exposure.
Yeah, too bad it's also
Humanity
really
seems
good
to
for like
have realized
photochemistry
this
as well.
only recently, and lead
Photovoltaics,
poisoning
nice.
used to be, and honestly still is, really prevalent. It actually contributed to the fall of the Roman Empire and dumped all of us down a little, since somebody once had the brilliant idea of putting lead in gasoline. It always
Well, the lead in the Roman Empire is a theory, but it is true that the Romans did used to have lead plumbing, and they did also have some they knew of a lead sweetener. I believe it was lead acetate, and I think it had something to do with the like making wine, which is slightly acidic, in ceramic that contains lead pigments or just has lead within it in general. And lead acetate is, for some reason, perceived as sweet, slightly sweet on the tongue, but, you know, does give you a nice dose of lead every time you drink it. So that part's true. Not sure if it's the entire reason the Roman Empire fell, but that's why it's a theory on Wikipedia. That's why this statement is not published in the journal Science. And also, yeah,
just how
oops, fucking up my
many
buttons.
things
Also, yeah, tetraethyl lead.
Empire and dumped all of us down a little, since somebody once had the brilliant idea of putting lead in gasoline.
Yeah. It was a great anti-knocking agent and made sure that your engine didn't bump when engines were really bad. But this is also why Gen X has a very, very high blood lead level compared to all generations, all other generations on the planet. They when Gen X got to see unleaded gasoline, that was like crazy. That was new. That was like good for the environment and for human health. Nowadays we're like, what the fuck? You were inhaling that many lead fumes? Whoever thought this was gonna be a good idea?
It always amazed me just how many things used to be made with lead, and even though it's slowly being phased out, some common items still contain it, albeit in disguise. Take this beautiful shot glass for example. I am sure most of us have seen one of these and wondered why they sparkle so much and make this cool sound.
Uh-oh. Uh-oh. I'm starting to think that the title of the video might have been clickbait. I get the feeling we're gonna make lead iodide, and there's gonna be lead in this glass. Lead iodide is nice and yellow looking, and could, you know, when crystallized, look kind of shiny like gold. It's not gold.
Well, it turns out that all this is due to a metric freak ton of lead in them. This so-called crystal glass contains a decent percentage of it, and it actually slowly leaches into whatever you're drinking, to the point where it's quite bad to store acidic beverages in lead glass for extended periods of time. All
It makes
this
middle-class
always
people
seemed
stupid.
just surreal to
Nice.
me, and ever since finding out about it, I wondered if it would be possible to free the lead from this glass and extract it as a metal. Now, nobody really did this before, at least on YouTube, and I was really curious if I could figure out how to do it, as well as how to use the recovered lead to cosplay ancient alchemists and turn it into quote-unquote gold.
Yeah, it's lead
Speaking of
iodide.
humanity's
God
age-old
damn it.
fascination with alchemy and leaving something behind,
I mean,
I
this is
really
still
want to tell
interesting.
you about The Last Book by Hungry Minds. It tells the
Yay.
story of Noah Kaplan, the last surviving Earthling, and being a hybrid of a personal diary and encyclopedia.
Alright, fine. This sounds cool. Even if it's sponsored, I am actually interested in this. But god damn it, it's just lead iodide. It's always fucking lead iodide. No one's ever actually making something cool.
The Last Book seamlessly fuses fiction with factual content, which is really exceptional if you ask me. It was created by an experienced team of over 50 professionals, successfully backed on Kickstarter and Indiegogo, and features 15 unique themed chapters covering everything from culture to science or entertainment. After reading it, I can assure you that it has something for everyone, being both educational and quite emotional as a recollection of humanity's story and the most important achievements through the eyes of the last surviving human being. It is also quite humorous, which I just love, and my favorite chapter by far was the one on entertainment, with all its references and beautiful hand drawings of the finest memes.
Oh, God,
Now,
that
apart
is
from
such a
this
clash
book's
of
amazing
generations
contents,
in
I
that
also
page.
found it itself to be something special,
I saw the
being
fucking
made
Jackie
from
Chan, what the
high-quality
fuck,
art
with the Giga
paper
Chad
with
with
all the
Nyan Cat
pages
with Grumpy
beautifully
Cat?
printed,
Like,
as well as a
really?
hard and somehow
No.
glowing in the dark cover, making it quite the premium collectible. It also serves as a perfect gift for readers, collectors, and anyone who simply enjoys beautiful and thoughtful books. If you want to grab a copy of The Last Book for yourself or a friend, check it out through the link in the description and use my promo code Chemistry10 for 10% off your purchase. Anyway, big thanks to Hungry Minds for sponsoring this video, and now back to cosplaying an alchemist. Extracting lead from crystal glass is much harder than it might seem, and even though it can be done on a tiny scale just by dripping something acidic like lemon juice onto it, I didn't want to hold back on the lead and decided to scale up. That's exactly why I reached out to my grandma, who owns quite the crystal glass collection, and after much persuading, she agreed.
Hi, Chris. No, I wanted to watch that sponsor because it seemed interesting at first, and then by the time I checked out, it was, by the time I checked out and thought it was no longer interesting, it was like, well, there's like 10 seconds here. Oh, well, who cares? Anyways, I get the idea because he also showed a little hammer smashing in the beginning of the video. There is going to be making small glass chips, throwing this in some sulfuric acid or some kind of acid, and then yeah, that extracts the lead out of the gold. I mean, you just need to powderize the lead to give, or the powderize the glass to get high surface area, and you know, then you can use acid to extract it, and then you get the lead, and you turn the lead into lead iodide. You add some sodium iodide, and boom, bam, there you go.
To give me this old piece. It looks to be some weird basket, and my grandma didn't really like it because of this ugly handle. To me, it just means more lead to extract, which is great, and as the first step in ruining a piece of art.
I would say I don't know why
For
the
fun-
lead added into this glass makes it more reverberatory, if that's a word. I mean, you can have lead ions replace the sodium ions, but I don't think that. I don't know, maybe because the lead is larger and it coordinates weaker to the oxygen, perhaps it makes for even more amorphous structures, so the sound travels through it better? I don't know, I'm not so sure about that, because it's usually the more dense an object is, the better the sound propagates through it. So I don't know. I couldn't take a guess. I couldn't have a good guess at it.
And profit, I wanted to crush it up, since being one solid chunk, the basket holds its lead tightly. To extract it efficiently, I needed the glass to be as close to a fine powder as possible, and to initially break it up, I first went outside. Now, I know that
I
this is
threw it
already
into the
quite
Nile
big for a
Red
chemist,
Penis Crusher
and
4000
after
that he
learning to
bought from
enjoy nature
Alibaba
for a while, I
$7,000.
smashed the hell out of the basket using a comically large hammer. I then got all the resulting glass chunks into a bucket and let my brother smash them up, which he really wanted to do for some reason.
Maybe
When
that
he
would have
was
been the better
done,
thing
I
to do
got
at
the
first.
glass into a
Like,
bowl
put it in a
and brought it
controlled
back to my
environment and
lab.
crush it.
These bite-sized shards were already
Bite-sized.
much better than the basket,
Yeah, but
but
they're
I
still
still
large.
wanted to make them into some fine sand. For that, I first set the bigger shards aside since they were slightly too big, and then used a sieve to separate the smaller ones from bits of paint that came off the bucket. Just for the record, I did all this in a fume hood, since even though there isn't much lead dust at this stage, breathing in any amount of this stuff is bad to say the least. Anyway, I weighed out 400 grams of the now paintless glass shards in a beaker, which was an amount I felt comfortable working with. To turn everything into powder, I couldn't really use a
Of course, this does also abandon the very small pieces of glass that managed to splinter off during the shattering process, but I think that's acceptable yields to not have plastic bucket pieces in your final result.
regular grinder and instead decided to boot up this absolute beast.
Oh, I know
As
where we're going. The
long-time
big ball
viewers might
mill.
recall, this magnum opus of DIY creations is a ball mill made by my dad, and it's honestly a great honor to use it in a video again. It will grind the glass by smashing it against some heavy steel balls inside a spinning coffee can. After letting
Call
it
this
actively
JoJo Part
destroy my
7, 'cause
hearing
those
for
steel
2
balls
days,
run.
I figured its job was done and was happy to see that most of the glass became
Wow.
this nice dust.
That's pretty
Quite a
powdery.
bit of it was unfortunately still in the form of little pebbles, and that's because my ball mill is basically an aggressive rock tumbler.
Yeah, it is the one thing about ball mills that is a shame. It's really good at just breaking off fragments of and turning really hard materials into dust. It's just really, really slow about it. It's basically an accelerated erosion process. And erosion is also very slow. So, like, look, it'll do the job. You're just gonna need to let it run for, like, several days.
Still, I figured that the amount of
Also, I don't know quite why it's yellow all of a sudden, but I'm guessing it has something to do with the defects, because maybe they'll get lead oxidizing, because because lead oxide is also a yellow color too. So it's just not the gold yellow that this guy's gonna go for with lead iodide.
ground glass I have is quite okay, and to extract lead from it, I first have to figure out how to dissolve it in water. You see, to extract any lead from this thing, I need to make all its components available for chemical reactions by getting them into solution, since as a solid, only the surface of the glass can react. As you may know, glass isn't really famous for dissolving in water, and forcing it to do so requires some really angry chemicals. I
you're
wanted
not
to
doing
find
that,
one
are
that
ya?
would dissolve the bulk of the glass as well as all its lead,
Oh, you're
and
actually gonna
after some
dissolve the
research I
glass?
figured that sodium hydroxide
Yeah,
should be
okay.
best for the job. This stuff is quite scary, often being used as a heavy-duty drain opener, and to
Yeah, I mean, okay, look, sodium hydroxide can give you burns, but like there is a good reason that pretzel makers can, like expert pretzel makers, still use sodium hydroxide. Like, and even homemade pretzels can still be made with sodium hydroxide if you want that really crunchety crust. But I guess the fundamental science is going to go for here is the lead 2 plus that's dissolved or interspersed in the glass. It's going to be with 2 units of sodium hydroxide. That's going to precipitate out. That's going to precipitate out 2 sodium ions. That'll be stuck with the glass and byproducts, and then a little bit of lead hydroxide. This is probably also a solid too. I'm not so sure how well this is gonna work, but I guess maybe the idea is that this will be the only bit of solid left, because how to explain this? So when I kind of showed that diagram of glass earlier, having just these 4 oxygens sticking out of the silica, silicon, and just kind of imagine that this continues going on. So when you have hydroxide ions, this is a very slow process because silicon oxygen bonds are already very strong, and so the existing ones here in the glass kind of don't really want to break that much. But because quantum mechanics makes things imperfect, and occasionally you'll get just like randomly electrons are like, well, actually, I feel like receding from the silicon today, and I'm going to go on to this oxygen. Hell, maybe this oxygen is like sodium stabilized already by like, what's in the glass. Actually, that would probably be hella unlikely to take its electrons back at that point. Well, maybe there's a nearby sodium on, like, another oxygen that's bound to some stuff here. And, maybe the... Because solid-state chemistry gets kind of weird. This is kind of maybe a little bit of a verboten rule, usually. But, say just randomly quantum mechanics says, okay, well, this bond wants to kind of go away over here, and it wants to... Okay, I keep forgetting I don't actually have an eraser on this pen. I should get like a new tablet type thing. That would be nice. This bond wants to go away, and it then just spontaneously kind of forms a bond over here. That's the pencil tool, not the pen tool. Then that leaves like some open spot here on the silicon for the hydroxide to get in there. And so that would create a new bond. So you then have like the silicon hydroxide thing kind of popping off of it. Repeat that enough times, you can isolate the silicon. This is really slow. You can dissolve glass in sodium hydroxide. It's also going to just take a very, very long time. So, I mean, it's a strategy. Not the best strategy, but eventually you will end up with like various like silicate species. Something kind of like this. And this is soluble in solution. So if this guy's procedure works out here, then he will be able to get some of that lead hydroxide that is soluble and or insoluble, and separate that out from the dissolved glass, which is now this sodium silicate, which is soluble. So not a terrible strategy, but definitely a slow one. Of course, this is to prevent him from needing to work with like really dangerous things, materials you can't just buy from a hardware store. But yeah, it's maybe the safest and most economical option.
try it out on my glass, I first got this steel can. It's like the only thing I can use as a container for the reaction, and after weighing out all my neurotoxic
Well, even then, we saw in the Explosions and Fire channel what molten sodium hydroxide can do to a steel can. It's not exactly impervious.
And in it, I added in 200 grams of sodium hydroxide. This is way more than necessary, but I really wanted to ensure that there is plenty of it to react. Anyway, I mixed everything real good, and to start the reaction, I had to heat the hell out of this mixture. The only thing I have that's powerful enough for this is my trusty gas stove.
So he's not actually bothering with the
And
aqueous
after
method
getting
at all.
the can onto it, I cranked up the heating. This made the sodium hydroxide start melting, and since the glass around it is a fine powder, the two can quickly react.
Just gonna try to do a solid phase thing with like maybe doing this in molten sodium hydroxide, huh? All right, that's brutal. Those are some pretty nasty conditions.
The main component of
your
the glass
steel drum
powder is something
turn to
called
rust.
silicon dioxide, which when attacked by molten sodium hydroxide quickly turns into sodium silicate and water,
Oh no, he actually got the formula right for that. No! Okay,
which in
I can
turn
correct
boils
that real
away as steam. The lead, which forms the other major part of this glass, is present as something called lead-2 oxide, and this stuff is also supposed to react with molten sodium hydroxide quite well, forming a chemical called sodium plombite.
I've never heard of that. Okay, so I guess my reaction here is wrong then. I can adjust that real quick. Go figure. PPO with 2 NaOH to that Na2PBO. Okay.
The products of both reactions should be freely soluble in water, which is exactly what I am looking for. Overall, everything seems to be progressing nicely, and to help the stove do its thing, I loosely covered the can with a lid and insulated it with some aluminum foil. Then the chemistry gods decided that everything was going too well, and the can exploded.
Yeah,
you can imagine
that
the
sounds
panic
about
attack
right.
I suffered when a bunch of corrosive lead sludge splashed all over my fume hood, and I was really lucky that I wasn't near the can when it happened. The funniest thing about this whole situation was that I didn't accidentally create some lead-based explosive, and it all came down to the lid, which somehow sealed itself shut and made a ton of steam buildup, resulting in this thing turning into a cannon.
What?
As you can imagine, cleaning up this mess was quite a feat, and I worked extra hard to get all the water-soluble lead into a dedicated waste container and not down the drain. The next day I was back in business, and since I didn't feel like hitting the weirdly inflated can again, I basically decided to start over. I luckily still had the big glass shards from before, and I used an anvil and a hammer to manually break them up. This really helped out my ball mill, which ground everything to perfection, leaving me with quite a bit of high-quality glass dust. I figured that I either go big or go home, and decided to process it all at once, so I combined it all with 250 grams of sodium hydroxide, and this time mixed everything in a blender to ensure even better contact between the reagents. Then I got the reaction mixture into a can and onto my good old stove, this time heating it really gently and without even thinking about using a lid. This went on for about an hour, with the color of the reaction mixture slowly changing into this beautiful orange. When I figured it was time, I got the can off the heat and emptied most of the still hot reaction mixture into a bowl, since I had a feeling that when it cools down, it'll turn into a hard brick. The lime yellow color of my product really surprised me, since I originally thought that it was all going to be a grey powder, and I guess that beautiful colors like these are your average lead chemistry experience. To get my lead from this forbidden matcha, I need to dissolve it in water, for which I got everything into a beaker. I then got back to the reaction can.
Now my question is probably going to be though, like if this is, both of these are soluble in water, the sodium silicate and the sodium plumbate. I mean, it's not that hard to separate them, I guess. It just feels like you maybe could have done the etching method maybe a little bit better, but it might have been easier, fewer steps, but I guess maybe it's slower. All right, you could probably just add like a lead iodide precipitate. All right.
Which still contained a good bit of brickified product, and to get it out, I poured in some hot distilled water. It turned out that it was a little too hot, resulting in tiny droplets of a water-soluble neurotoxin spraying everywhere, which
Hell
was
yeah.
just splendid. I was more careful adding the next portion of water and was ultimately able to tame this thing. I poured the resulting solution
A
into
leaky
the
can.
beaker containing the rest of my product and repeated this process a few more times, eventually dissolving everything.
But
This
congratulations,
left
you're
me with
making,
a
like,
muddy solution
prehistoric
containing a
pigments.
good bit of sodium plumbite, sodium silicate and unreacted sodium hydroxide, as well as a bunch of this insoluble suspension, which had to be some impurities from the original glass. I really wanted to remove this mud and proceed with a clear solution, but it turned out that filtration wasn't really an option. To remedy this, I basically left this beaker to sit for a month, which made all the mud sink to the bottom. I got all the resulting orange solution into a bottle for
Love lead
storage,
to the brain
and after
damage.
finishing the Rabrin
favorite
video,
movie.
came back to it and poured it all into a clean beaker. It was now time to start worrying about how I am going to get my lead from this forbidden mango juice, since I couldn't find any procedure for this. As it turns out, extracting
iodine
just the lead
salts?
from my solution without pulling any other junk along with it is no easy task, and at that point I was thinking about putting this project on indefinite hold. Fortunately,
really?
in the midst of a midnight Wikipedia surfing session, I experienced chemical enlightenment. It turns out that there is one very obscure and incredibly toxic chemical that can separate lead from my solution like magic and miraculously is commercially available. It's called sodium sulfide and it comes as these yellow platelets which...
That's a decision for sure. So yeah, sodium sulfide is actually a fairly it is actually a fairly hazardous chemical. Not only is it extremely basic, so very corrosive. On contact with water, it produces hydrogen sulfide gas, which is kind of commonly that rotten egg smell. It's not the rotten egg smell in like natural gas that's piped into your oven, but it is a one of those rotten egg smell chemicals that is as toxic as carbon monoxide. So sodium sulfide is not something you typically want to use or fuck with. I still maintain that this could have just been done way more easily by just acidifying the solution and then adding like sodium iodide to it. Like that is a classic precipitation reaction. It'll get you lead iodide, and I don't think silicon and iodide bond very well either, so it's not like you're gonna get a silicon iodide product. So still not sure why we had to take this route, but
really
he's the video maker.
Reek of rotten eggs and are generally a pain to work with. I wanted to get over using this devil's table salt as fast as possible, so I quickly got 140 grams of it into a...
Oh yeah, and he's probably gonna do this in a second, explain it, but basically the idea is that the sulfide wants to the sulfide wants to bind to the lead more than the oxygen does. So, given lead in solution, you will get lead sulfide to come out of there. Preferentially over oxygen or a lead oxide of some kind. So I'll wait to see if he acidifies this first, or if you know, he's just gonna go straight with another solid reaction before I write anything down.
A beaker and dissolved it in a bunch of distilled water. This made a weirdly green solution, which I then slowly poured into my lead beaker. Right away, a spongy black precipitate started forming, and this whole thing looked quite interesting. Now, what the hell is this precipitate, and why only sodium sulfide works for this? Well, the precipitate is a compound called lead-2 sulfide, and its formation is what allows me to selectively separate the lead from this chemical mess. You see, lead absolutely loves to bond with sulfide for some reason, and because the resulting lead sulfide is insoluble in water, it crashes out of solution, leaving all the other stuff untouched. This is yet another example of...
Okay, hold on, let me get the overall reaction here. Let me think about it. So I'm gonna erase the countercat ions, because that's probably not playing much of a role in this reaction. The sodium's probably... Oh, now I gotta fix my drawing. Right, there we go. Okay, so the sodium probably leaves the lead oxide stuff alone. So this is probably going to be a 2-. You have your H2S here. The H2S that's kind of floating in solution as a loose gas / dissolved compound is, part of that. It's vaguely acidic, so you could probably get some of the oxygens with the charge here, attacking the hydrogen. So you're gonna end up with kind of an intermediate step of something like PB, with like some. This is a little bit generous, a little bit kind of hand wavy as far as what the actual chemistry is doing. It probably wouldn't double dissociate like this, at least not immediately. It'd probably use another hydrogen sulfide, but we're kind of being generous here. So this gets us an S2- ion, and this probably wants to rearrange to form water. So this can go and attack here. This electron goes back here. You get like a lead oxide in solution. Then you're left with PbO plus S2- plus H2O. And then if we did want to account for the sodiums being here at the beginning, we could have Na plus here. It's not Na2 plus, there's just 2 of them. Let me fix that real quick. Two Na plus. So you have 2 of these still around. 2 of these still around. And with the aggression of this S2- ion, and it wants to be on the lead, it'll attack the lead, it'll bump off the oxygen will go after the sodium. And again, being a little hand wavy about the mechanism, but basically that's how you end up having lead sulfide. And sodium sulfide kind of back again, I guess, from the original reagent. Yeah, again, hand wavy, weird stuff. This probably would then go back to like attack the water and form like a sulfohydride, or yeah, it'd probably form like, instead of hydroxide being OH-, be the sulfur version SH-, and those would find sodium ions, and that would be a byproduct. And there's a lot of possibilities of like what's going on there. But the point is that we get lead sulfide out of this by adding sodium sulfide.
Lead having some funky properties, and with all of it as this black suspension, I could finally separate it out. For that, I wanted to use a vacuum filter, but this turned out to be a terrible idea, and the only thing that ended up working was this beautiful creation. It's a kitchen strainer coupled with this gigantic sheet of filter paper, as well as a bowl.
Gravity filtration.
It made for a really pleasant filtration, allowing me to quickly get rid of excess sodium sulfide, as well as wash my precipitate with copious amounts of distilled water to remove most impurities. When I felt that my lead sulfide was pure enough, I let it air dry for a week, which greatly reduced its volume, leaving me with some premium mud. To turn the stuff into lead metal, I again had to improvise a bit, since I couldn't find any records of people doing this before in a lab, and all I managed to find were descriptions of how this is done in.
Okay, so it's starting to make more sense why he did it this way. Because he specifically wanted to get lead as his first objective, and then the bonus objective later was to, how do I make this into clickbait? Ah, yes, make it look gold and make it lead iodide. So this makes a lot more sense, because there's known methods for lead sulfide back into lead, whereas lead iodide would be a lot harder to do that with. Mostly because you can make sulfur into gases like sulfur oxide, and you can't do that with iodine very well.
Industry. That's exactly why I decided to just embrace the industry and showcase how big companies extract lead from lead sulfide ore. The first step is something called roasting, And it isn't about telling lead sulfide how useless it is, but rather putting it through literal hell. For that, I need a suitable crucible, and I decided to go with a high-tech cut food can, which I cut in half using a handsaw. I loaded all my lead sulfide into it, and again had to use a gas stove to heat it,
I love
but
steel
since I
cans.
didn't record this in my main lab, I had to use this one. It for sure doesn't have as much soul as the old one, but it's much stronger, and roasting the sulfide using it was a walk in the park. Now, this roasting step allows oxygen from the air to react with lead-2 sulfide, forming lead-2 oxide and sulfur dioxide. The sulfur dioxide is a mighty toxic gas, which is why I do all this in a fume hood.
Also, I guess if you might be wondering, I can elaborate on this a little bit further. Let me create a new page here. Given that I said, so much that sulfur really wants to hang out with lead much more than oxygen does, you might be wondering, well, okay, why then does oxygen end up displacing sulfur in this reaction? If sulfur wants to stay so much, then why does it leave? Why is it so unfaithful? Well, that's because this reaction is basically just not reversible. Even though the sulfur would much prefer to stay on the lead, once you basically get once this reaction goes even forward for one molecule or unit of lead sulfide, it turns into sulfur dioxide. That's a gas, and that just flies off into the atmosphere. And while oxygen is also just a gas that theoretically flies off into the atmosphere away from the lead sulfide, most of the atmosphere is oxygen. So it's just statistically likely that forms an SO2 molecule. It flies off, never to return. You can't get that back. It will never turn into lead sulfide again. Surrounded in oxygen, even if the reaction doesn't want to work, it's just gonna keep trying and trying and trying again. Oxygen is a gambler. 90% of all oxygen molecules quit before they win big, but 10% of oxygen molecules, they make it onto the lead and they stay there, and sulfur gets kicked out. Poor loser sulfur, right? But that's essentially just what's going on here. And then from here, it's a very easy, well, I won't say very easy, but, there are reducing agents he can use to get lead oxide over to just straight out lead, and boom, project done.
And the lead-2 oxide is the exact same stuff that was originally in the glass. It's quite funny how this project kind of loops in on itself, with me doing all this work just to end up with purer starting material, and this is honestly the perfect example of how tedious chemistry can be. Anyway, after roasting the absolute hell out of the can for half an hour, I figured that I had roasted it enough, and I ended up with this grey lead-2 oxide powder. It was incredibly dense, and I managed to make 54 grams of it, which is quite okay. Now, it isn't completely pure,
Also, lead oxide is white.
Since it should be a beige powder, but honestly,
it was
I don't
a pigment
care.
for many years.
It's still more than pure enough to make some lead
this is
with,
contaminated
and for that,
with carbon
I have to get
that
rid
is
of the oxygen part of this
ubiquitous in
thing.
the steel.
There are several ways to do that, and since I wanted to do this just like the industry, I decided to use 3 grams of activated charcoal, which is basically just extra
I think
pure
you've
carbon.
got enough in your lead, my man.
With my lead oxide, I ground the two together in a blender, creating this neurotoxic powder of death, which I then loaded into a ceramic crucible. To heat this thing up, I got this electric furnace, which is a part of my legendary equipment squad, and despite looking like it wants to die,
it's that
will
Hellburn,
still
is
serve
that,
me. I loaded the
fire
crucible
owns and
into it
misuses.
and set the temperature to around 1100 degrees Celsius. As everything warms up, the lead-2 oxide should melt and subsequently react with the finely powdered carbon to make carbon dioxide gas and
Very
some lead
simple
metal,
reaction.
which should flow to the bottom of the crucible. I let everything cook for 2 hours and then let the furnace cool down overnight. The next day, it was time for the moment of truth, and upon recovering the crucible, I discovered that it somehow welded itself shut. This yellowish crust responsible for that was probably some...
I laugh because it's relatable. Chemistry just has this habit of well, the chemistry worked, but the trade-off is now that the physics of everything is gonna tell you to go fuck yourself. Yeah, that's how it is. Now you gotta pry that thing open.
Unreacted lead oxide, and the only way for me to open this thing was to ever so gently smack it with a hammer. After some more smacking, I managed to uncover this small metallic pack which had to be lead, and I was intensely happy that in the end I managed to make it. The
Gotta
yield
wash
was
off all the
also
carbon.
surprisingly high, being 41 grams or around 81% from the starting lead oxide, which justified doing all this work at least a little. Now, my lead isn't super pure, and I can tell because it's quite brittle and formed these beautiful crystals upon cooling, which doesn't normally happen with pure lead. I am honestly okay with that, considering that I made this piece of metal from a glass basket, and now I can finally
time to
do
melt the
what
hell out
I've
of
been
it,
looking
purify.
forward to the most in this project, which is turning my lead into gold.
Okay.
To start, I got a few of my homemade lead crystals into a beaker, and after wetting them with some distilled water, added a few drops of concentrated nitric acid that I made in a previous video. It reacts with the lead to form something called lead nitrate, and after letting this mixture sit for a day, I was left with this slightly cloudy lead nitrate solution. I diluted it down with a bunch of distilled water and set it aside for now. I now need to prepare a second solution, for which I got a big beaker with a magnetic stirrer onto my hot plate, and after chucking in like half a liter of distilled water, sprinkled in a bit of something called potassium iodide. This resulted in a colorless solution, which is really quite boring if you ask me. However, when I combine this solution with my lead nitrate solution, a yellow precipitate
Wow, look at
appears,
that.
which is much cooler. It still ain't gold though, and to fix that I started heating it, and when the water was nearly boiling, the yellow color magically disappeared. I then took this clear solution off the heat and applied some sexy lighting, which made these golden flakes suddenly appear and slowly move around
yes.
in this
The best way
sparkling
to change
golden
the color of
rain.
a chemical.
Now,
Change
this
the color
of
of the
course
light
isn't
on it,
actual
shining on
gold,
it.
since without a particle accelerator you can't really make any, but I think that the chemistry that makes this fake gold rain possible is just as cool as real gold. You see, when I combined the lead nitrate and potassium iodide solution, they quickly reacted, forming something called lead iodide in the form of this fine yellow suspension.
Fun fact, this is
Lead
a
iodide
common
is
Gen Chem
normally
reaction I
quite
once had
insoluble in
to
water, but
TA
if the
over
water
in
is hot and there
college,
is a
or
lot
grad
of it, some lead iodide can dissolve. In solution, it is completely colorless, and when I force it to precipitate back out by cooling everything down, instead of being an ugly suspension, lead iodide turns into these beautiful crystals. This whole thing is called the Golden Rain Demonstration. It's one of my favorite experiments, and I still
That
can't
is
really
one
wrap my
word
head
off from
around
being a
something
very
so
dirty
dangerous
title.
and common as lead having such diverse and interesting chemistry. What's even cooler, this experiment might
Heck,
as
it's
well
even
have
worse when
started
rain and
alchemy,
shower are
since
synonyms
lead
as
and
well.
iodide were quite easy to come by even thousands of years ago, and I bet that the person to first discover this thought that they turned lead into gold. Since alchemy is what ultimately became modern chemistry, this experiment holds a special place in the heart of many chemists, and if anything made humans want to learn more about the substances around us, it
This
has
doesn't
to be
really
things
hold a
like
special
these.
place in my heart.
Now, what I find really interesting about lead iodide
I grew
is
up
that
in an
it
age where
doesn't just
particle
kind of resemble
accelerators-
gold when floating.
When I grew up in an age where particle accelerators exist and it's actually possible, though very expensive, to turn real lead into real gold, I'm maybe a little nonplussed about lead iodide. It's been done.
In water, since even after being filtered out and dried, this stuff
It's very
is like
pretty,
the
at
best gold ripoff I've ever seen. It also has many other cool properties, like turning red when heated, and I think that I
Red
couldn't
glass.
ask for a better ending to this project. Putting up with explosions, fire, and neurotoxins
Explosions
to
and
turn
fire?
an ugly glass
Hold on.
basket into
Say
a
that
heavy
again.
metal and a golden milestone of ancient chemistry was really quite the journey, and I think that it has been more than worth it. It's projects like these that really make you appreciate the awesomeness of chemistry, and I want to
Tic Tac
sincerely thank
container
you all for
to
watching,
hold it.
since this video just wouldn't be possible without
Fair
your
enough.
support. In terms of what I want to do next, I have a ton of amazing projects planned and want to follow up.
Alright, so while that video wasn't as interesting as I thought it was gonna be, it's at least a pretty cool demonstration of basic chemistry, which, you know, for an audience who mostly watches me for Mega Man and video games, that might not be the most familiar territory in the world. So it's accessible. I'll take it. I'll take it. And you'll take it too, because I made you watch the video. You have to take it. All right, the next video is probably going to be very exclusively for me then, because I am most interested in this one. Although I think the blue color might be interesting as well. So let's get a refresh so we can take a look at that thumbnail for this video. Trifluoronitrosomethane, CNOF3. So this is a molecule I actually know about, not from my research or my schooling in any way, but I know about this molecule because I'm a nerd and I wanted to think about like some D&D world building type stuff. And so I'm pretty sure I found out about this because I thought of, what are natural blue gases? What are real blue gases? I guess is the better question. Because, you know, if I'm building a D&D world, I want it to be chemically accurate because I'm a science nerd. And so I found out on Wikipedia this is like the most common entry, like this is a blue gas, trifluoronitrosomethane, which, you know, supposedly would be blue because of the very high charge polarization on this molecule. And due to how charge polarization will mean a fairly large energy gap within the molecular orbitals of a molecule. We can kind of simplify this being the lowest occupied molecular orbital, or lowest, hold on, no, sorry. Wrong placement for that. The lowest unoccupied molecular orbital with no electrons in it, and the highest occupied molecular orbital with some electrons in it. Having a charge separation where you have a very strongly... Let me think about the electron distribution on this for a second here. Because CF3, that's very electron withdrawing. Oxygen's also pretty electron withdrawing too, but not nearly as much as this. So you're going to end up having a negative going in this direction. Positive slightly on that side. And also just like there is this kind of like, how to put... There's almost like a competition for like some of these electrons. Like probably this nitrogen electron is the most available to donate one way or the other. And it's not like it can directly donate the electrons because directly donating here to make another carbon-nitrogen bond, that's not allowed. You can't have 5 bonds on a carbon. Donating it here to make a third bond to the oxygen. Oxygen can have 3 bonds at a time, technically. But given that the oxygen is in this state with its own 2 electron pairs, that would go over its 8 that it wants in its circle. And so adding 2 more on there is just not allowed either. So you kind of have this frustrated lone pair that's like, well, where the hell do I go? I'm being tugged between 2 very competitive electronegative areas. And, you know, this is going to cause the electron excitation band to be like... orange light. In fact, I can use the color orange here to maybe demonstrate this. That's not orange. That's yellow. That's salmon. That is kind of orange. Hold on. There we go. We can be like, this is orange light. That's not very well drawn, but hold on. I could draw an arrow better than that. There we go. Orange light comes on in, causes electron to go up, become excited, go into this occupied orbital. Absorbing orange light should mean that, you know, subtractive colors in play. The gas is going to be blue as a result. But interesting. This video claims that this picture is fake, and the gas is in fact not blue. I have not purposely looked at Wikipedia since this video, so... I'm not entirely sure if the Wikipedia has been updated or what this gas actually looks like. I'm hoping that this is correct, although I'm seeing there's maybe a follow-up video in the corner here, which, well, maybe we'll have to watch that as a bit of a squeakquel, huh? So I'm going to save that to the React Later playlist, so that way we can actually take a look at it. Maybe not tonight, because we don't have the time, but perhaps the next month kind of thing. Maybe, in fact, I'll do it sooner than one full month in between. How about that? Anyways, let's take a look at this.
About 3 years ago, I wondered, are there gases in every color? What I quickly found out was that there are lots of yellow, orange or brown gases, but practically nothing blue. And I would bet you have never seen a blue gas either. The only blue gas that some people might know is ozone. But even at very high concentrations, you have to look closely to notice the blue tint.
And, you know, try not
The
to die
reason
either.
almost nobody has ever seen a blue gas is
Not to blow
that
up.
the blue ones are all very obscure compounds.
Remember with the one scene with Mr. Bean went back to school, he blew up the entire chemistry class with a blue substance. I don't actually remember that scene. I didn't watch a lot of Mr. Bean when I was younger. But, yeah, wouldn't doubt it. I don't really know any explosive blue substances of my own. Actually, no, that's a lie. There are copper substances that, yeah, copper perchlorates, but, like, there's something from explosions and fire, unlike copper. Copper nitrotetrazoles, that's what it is. Those are highly explosive, but also unlikely. But, yeah, you know, there's some realism there.
You can't
And they're
even
blue.
find a picture of one online. The two most well-known blue gases are hexafluorothioacetone
Oh, I
and
never heard of that
trifluoronitrosomethane, simply because they are the only ones that have a Wikipedia article. And now look at this. There's even a photo of trifluoronitrosomethane. Isn't that a beautiful gas? But what if I told you that picture is a lie? When you search for images of chlorine gas, you find a photo that looks suspiciously similar
That is
to the
suspiciously
one
similar.
of trifluoronitrosomethane. If you compare the reflections on the flask, you can see it's clearly the same photograph, with all the yellows swapped for blue.
Look
So
at these
nobody
photographs.
actually knows what this gas looks like. The moment I discovered this fake picture, I knew I had to make this gas myself to find out what it truly looks like.
Maybe replace
About a
Wikipedia's
year
picture.
ago, during my master's, I did an internship in Professor Kraus' fluorine lab in Marburg. I managed to convince the PhD student Björn to let me use the last days of my internship to try making that gas. This was the result of that attempt. If you look close,
blue in there.
you can just make
It's
out
blue-green,
a bluish
it's like
tint.
teal.
But it wasn't the result I'd hoped for. Sadly, my internship ended and I had to start working on my
If you compress it, you could probably get a
master's.
pretty dense
For a
color
whole
there.
year, the idea of this project wouldn't let me go. So I asked Professor Kraus whether I could try again. A few days after I handed in my master thesis, I got to work. The plan was to make the blue gas within a week, purify it, analyze it, and above all,
That's a
take
tall
a new
order.
photo to
mean,
finally
you know the
replace
reaction,
the fake
but-
one on Wikipedia. I didn't know whether the experiment would succeed this time, but if you don't try, you've already failed. So, let's get started.
It's hard to plan on
This
actually getting
is what
everything
the
done in
structure
1
of
week.
the blue
'cause,
gas,
wow, lab conditions change quick.
trifluoronitrosomethane, looks like. The first step is to make this part of the molecule. That piece actually comes from a compound called trifluoroiodomethane. The problem
Yodo.
is you can't just buy
Not the English
trifluoroiodomethane.
pronunciation, but
It's expensive and hard to get. So I first had to make its precursor, silver trifluoroacetate.
Ooh.
To make that, I needed 50% trifluoroacetic acid, but all I had was the anhydride. Luckily, that's not really a problem,
Okay.
because I could just add it to water to get the acid.
All right, so we're actually jumping right into the chemistry here then. So let's see. Starting off with the trifluoroacetic anhydride. So I'm going to do a little bit of shortening in what I'm drawing here. Let me get the black paint back up. Okay, so F3C and this, and then CF3. He managed to have this anhydride available. when you add water to an anhydride like this, what happens is that the lone pairs of electrons on the oxygen, they go and attack the carbon-oxygen double bond here, which forces electrons back up onto the oxygen, and then, given time, forces it back down, which, hold on, I suppose I should draw this, maybe. This would be enlightening for those unfamiliar with mechanisms. You have this intermediate species here temporarily. So, let's see, oxygen minus. Then you have the CF3. And then you have the water that just attacked. 2 plus. I'm going to skip over the protons or the hydrogens transferring over, just to kind of speed things along here, because it's not a very critical idea. Or what am I trying to say here? Just because there's a lot of them that are going to happen, and that they're happening like constantly, and it's just it's just going to slow things down. It's not really, too important to focus on. What we want to focus on here with the mechanism happening is having this oxygen gets a proton at some point. Maybe it gets it later in the process, maybe it gets it earlier, or maybe it gets it at this stage. And you have the O- up here, you have the new hydroxide group, and you still have this CF3. So the protons do a little bit of moving around. This negative wants to go back downwards. If it can't get a proton, which it will get in some capacity, but again, we're kind of glossing over potential for where the hydrogens can go. Comes back down, moves this bond back into this oxygen here, and thus that makes 2 units of this F3C. Oops, let me draw that double bond a little better. OH. So water splits up these anhydrides by basically oxygen attacks one of the ketone groups, shuffles some hydrogens around, and then that causes it to split at this bridging oxygen, forming 2 identical trifluoroacetic acid molecules. He's then going to need to make the silver version of this, so I'm guessing that he's probably going to add some kind of like silver hydroxide type agent. The hydroxide will itself pull off one of the hydrogens, so I'm going to just kind of represent that as H2O falling off in one direction. Then you end up having a, let's see, silver with, draw it, I guess, with, bump, 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 bump. CF3 here. And just so you're aware, these like little dashes are kind of meant to represent that like you have electron density kind of flowing between these 3 atoms rather than just localized to 2 of them. 3C. So that's a silver iodide or a silver triflate compound. Then, as mentioned before, you can add an iodide. You can replace some of this stuff with iodine. Although I'm not too sure how that works necessarily, so I'm going to hold off on that. But the general idea is that you're going to then get rid of some silver oxide, Ag2O, perhaps in multiple units of silver, and then you'll end up with a F3CI. Okay, there we go. So let's see how he does it.
So I filled a 250 milliliter round bottom flask with deionized water and then slowly added the trifluoroacetic anhydride while stirring. This reaction gives off a lot of heat, enough to make the water boil.
Oh yeah,
To
this is a
prevent
highly
that, I cooled the
exothermic
flask in a
reaction.
water bath. Once I
It
had
wants
the
to
acid,
break
I
so
added silver
hard when you add the
oxide.
water.
The silver oxide neutralizes the acid.
Ah,
forming
okay, so he's adding silver oxide instead of hydroxide, so I can adjust my diagram as such.
silver trifluoroacetate and some water. I also expected this reaction to get quite hot, since neutralization reactions usually release a lot of heat. But interestingly, I could barely feel any temperature rise. After adding all the silver oxide, I was left with this brown suspension that looked almost like mud. Now I just had to remove the water to get the product I wanted. To do that, I connected the flask to a cold trap, cooled with liquid nitrogen, and pulled a vacuum on it. In the cold trap, the water freezes out, preventing it from reaching the vacuum pump. What was left behind was a beige-gray solid. In theory, it should have been colorless, but impurities in the silver oxide gave it this gray color. This silver trifluoroacetate is the direct precursor to trifluoroyodomethane. If you heat it with iodine, you get trifluoroyodomethane, silver iodide, and CO2. But a lot of the iodine vaporizes and never reacts, so you need an apparatus that separates the trifluoroyodomethane from both CO2 and iodine vapor. Silver iodide isn't a problem, it stays in the flask as a solid. So I built this setup. The reaction flask is connected to 3 cold traps. The first trap is chilled with ice water and catches most of the iodine vapor.
Again, I guess just briefly explaining over the mechanism of just like, you have this silver triflate, you have a source of heat, and something to replace the triflate and silver when it goes off as silver oxide. The iodine will basically come in, replace the CO2 group that this is a CO2 group, that's a carbon dioxide group. Replace that. The oxygen, one of the oxygens can go with some of the silver. The remaining oxygens can go with the carbon that's attached to, and one of the iodines comes in, replaces, and the iodines replace the CO2 group there, and therefore you get your nice F3CI option. No gloves is powerful. Shit, I haven't even noticed. Hold on. Let me look at his poor form. Well, okay, he's got gloves there, at least right now.
So I built this setup.
He better keep those gloves on.
The reaction flask is connected to 3 cold traps. The first trap is chilled with ice water and catches most of the iodine vapor. The second trap is cooled with dry ice and isopropanol and reaches roughly -75 degrees Celsius. That's where the trifluoroyodomethane condenses. The third trap is a safety trap, also dry ice cooled to catch anything that makes it past the second trap. Behind the last trap, I put a mercury overpressure valve, because CO2 won't condense in the cold traps and needs somewhere to escape.
That's actually a really cool setup, all things considered. I've never seen somebody have to set up 3 cold traps, especially one of which is different from the other 3, to actually get their compound. But that is actually really interesting, where like you're getting your reaction, the product you want, this F3CI, is a highly volatile substance, so it's going to, with the very hot reaction, it's going to flow out of the reaction tube, and you need to find a way to catch it, but you also need to make sure you're not catching, remaining iodine crystals that are, like, just not reacting with stuff, so you need to have that to capture one thing, and then you need to have the cold trap to capture your product. Cool chemistry, honestly. This is the kind of stuff that I love. This is the stuff that I would love to be doing right now.
Otherwise, the setup would burst.
It's so clever.
Before I could add the silver trifluoroacetate to the flask, I first had to grind it into a fine powder.
Yeah, let me just find all the money
After
and all
that,
these chemicals.
I added iodine to the mortar and thoroughly mixed the two together.
Go join a research
Since this
lab
reaction
and
happens
ruin,
between a solid and a liquid having as much surface area as...
If I join a research lab, I won't have time for you guys then. You wouldn't want that. Use yours. Thanks.
I added iodine to the mortar and thoroughly mixed the two together.
Little iodine balls.
Since this reaction happens between a solid and a liquid having as much surface area as possible,
That's the usual form of iodine I'm used to seeing, but
mid-grinding, I realized the 250 milliliter flask I planned to use was too small. So I got a 500 milliliter flask and used that
big boy
instead. Then it was
Look
time
at that
to prepare
carcinogenic
the cooling
dust.
mixture. Before adding the dry ice to the isopropanol,
Man, you could really use some
pre-cooled it with liquid
cryogenic
nitrogen
gloves.
until it had a syrup-like consistency.
What?
That way,
what? Syrup?
What?
How'd you get syrupy
liquid
liquid nitrogen?
Prepare the cooling mixture. Before adding the dry ice to the isopropanol,
Oh.
I pre-cooled it with liquid nitrogen until it had a syrup-like consistency. That way, far less foam forms because the dry ice is added to already cold isopropanol.
Interesting. I mean, that's a cool thing from a safety perspective. It's definitely not a practical one because you're using a stronger cryogen to get down to a colder cryogen, or less cold cryogen, but you know, it's a good idea. Times guy in your lab started pouring noxious chemicals down the drain, no gloves. Why are you telling me this? I don't. That's a bad fucking practice. You need to stop that.
After filling the first trap with ice and the other two with dry ice isopropanol, I heated the reaction flask with a heat gun to roughly 200 degrees Celsius. After a short while, the iodine started to vaporize and you could see gas escaping at the overpressure valve.
No, my
That
reagent.
was CO2, which won't condense in the traps because its boiling point is too low. The gas evolution is a great visual cue for the reaction progress. When it stops, the reaction is done. After a while, beautiful iodine crystals formed in the apparatus.
Pretty.
I kept
Clogging
heating
your
the flask
pipes.
until no more gas was escaping at the overpressure valve, and when I removed the doer, you could see liquefied trifluoroiodomethane in the second trap. As you can see, it has a violet tint from trace iodine impurities. At this point,
impurities.
the gas should have been
not as
washed
cool.
with a sodium hydroxide solution and then distilled to remove impurities. I decided to skip that wash since the tiny iodine traces didn't bother me and won't cause any problems in the next reaction. Spoiler, that decision would come back to bite me later.
Why do chemists not want to purify their stuff in between steps? I know it takes time, but am I the only chemist who is not satisfied with having a slightly dirty product before trying the next reaction? Like, look, I get sometimes, like, 2 reactions, you can just keep going, the byproduct isn't going to affect your reaction, and, like, maybe you can save some time and, like, clean everything all up at once. But, like, more times than not, you try to outsmart the chemistry will win. Just work with the chemistry. Don't work against it. Don't be your own biggest enemy. God.
Trifluoroiodomethane has a vapor pressure of 5.4 bar at room temperature. That means if you don't keep it cold enough, it will build enough pressure to blow up ordinary glassware. So, to store it without constant cooling, I needed a proper gas cylinder. I chose a small one
Fabricating
and
your own
fitted it with a
gas
needle
cylinder.
valve.
Damn.
To make sure it was completely airtight,
Can't say I've ever done
I
that.
hooked it up to the fluorine line, pulled a vacuum, and watched to see if the pressure held. It did, so I connected the cylinder to the cold trap using an adapter. To transfer the trifluoroiodomethane from the trap into the cylinder, I needed to evacuate the whole apparatus first. Otherwise, I would condense air into the cylinder. To avoid losing the trifluoroiodomethane during pump down, I replaced the dry ice doer under the trap with liquid nitrogen, so
make
the
it as cold as
trifluoroiodomethane is fully frozen solid. Once frozen, I can pump down the system
Are you not going to show us
without
that
the
nice pink solid?
trifluoroiodomethane evaporating. When a good vacuum was reached, I cooled the cylinder with liquid nitrogen and removed the doer under the cold trap. After a short while, you could see the trifluoroiodomethane boiling and it condensed into the gas cylinder.
Okay, so gas going
After there
first
was
now,
no
letting it
liquid
just
left
nature
in
take
the
its
cold
course.
trap, I closed the needle valve and removed the cylinder. To show the liquefied gas a little better, I condensed some of it into a specialized glass vessel that can withstand the pressure even at room temperature. Once the trifluoroiodomethane was ready,
that iodine
I
in
only
there, though.
needed one more building block for the final molecule.
Okay.
Nitric oxide.
Oh.
Nitric oxide
Simple
is
enough.
a colorless but also quite toxic gas. Still, let me show you something interesting. When I connect the nitric oxide cylinder to the same cold trap I used earlier and fill it with the gas, you might notice something unexpected. A faint orange tint. But wait, didn't I just say nitric oxide is colorless? That slight orange hue actually comes from tiny traces of nitrogen dioxide. a contamination that's almost impossible to avoid. As soon as I open the trap, the gas reacts with the oxygen in the air and instantly turns into a deep orange cloud of NO2. That's the gas I mentioned earlier. To make the blue gas, according to Wikipedia, all I had to do now was shine UV
My
light
best
onto
source,
a mixture
Wikipedia.
of trifluoroiodomethane and
UV
nitric
light,
oxide.
okay.
It also mentions that a catalytic
Didn't know
amount
that
of
would happen.
mercury is required.
Mercury?
A catalytic
Okay.
amount means a small amount. To irradiate both gases with UV light, I will fill them
Alright,
into
I was
this
going to
6
write a
liter
reaction
flask,
for this,
which
but I have
can
no
then
fucking clue
place in
what the
front of
mechanism would
UV
be at this
reactor.
point.
It's equipped with several low-pressure mercury
All I would know at this point is that the radical on the nitrogen is probably what's going to attack the carbon iodide bond, or maybe the carbon bond after the mercury gets involved, and maybe the mercury sequesters some of the iodine, and then the iodine forms back together to form iodine, the molecule, instead of mercury iodide, and then the mercury refreshes, and then the nitrogen gets in there, and bam, gets in on the carbon. But that's, yeah, it's a little bit crazy. Now you suggest SN2 chemistry, which would be the as simple as, you know, something like this, where you have the lone pair attacking the carbon iodide bond from the back. But I would say, and I know you're probably just joking, but I would say that the size of the fluorines is just simply too much for the nitrogen to reasonably get in there. You're not gonna, you probably won't have SN2 unless, unless the idea would be that the UV light causes the fluorines to flex in such a way that they move away. But I would say that's probably not the case, because then why the mercury catalyst? The mercury is necessary somehow. And so if the UV light was simple enough to move this away, then that's probably not what's happening. Also, you know, radicals want to react first, so that's probably doing something like that. I just know, I just guess that that's happening. My guess is there's maybe like a, you know, a stage where like you have this F3CI, this bond interacts with like a mercury. There's like a oxidative addition that happens here. Get mercury attacking here. You get this iodine bond over here. So you get the CF3 mercury iodine fragment. Then with the assistance of some UV light, you probably end up splitting, like, you probably like make this bond a little bit weaker, perhaps. Get the NO in here, helps split this off. Probably end up getting, that's how you end up getting your F3C NO compound. And then your mercury kind of have this weird, like, mercury iodide radical. What is that? And then that probably ends up having, like, well, another F3C is now coming on by, and then that gets attacked here. And so now the F3C does something like this. Maybe it then goes into the mercury and coordinates, or maybe the two iodines end up going away from here. There's a lot that's like happening past this point that is like, this is so speculative, I couldn't imagine. But I imagine this is how the mercury plays in somehow, and the UV helps with the catalyst, maybe. Catalyst? That's a new word. Uh-oh, Crash is getting tired.
lamps that give off quite a bit of ultraviolet radiation. I wasn't entirely sure whether high pressure or low pressure mercury lamps were the right choice for this reaction, but since I only had the low pressure ones available, I just hoped they would work. Before filling the flask with the gases, I added the mercury. Mercury is a toxic metal and the only metal that is a liquid at room temperature. I chose the catalytic amount by eye, thinking it would be enough. Maybe I should have read the original scientific literature before doing the synthesis.
Why on earth, when you say you have only a week in the lab to make this blue gas, do you take this extra shortcut too? Just read the damn paper.
After adding the mercury to the flask, I connected it, along with the nitric oxide and trifluoroiodomethane cylinders, to the fluorine line. I wasn't actually working with fluorine, but that line has built-in pressure gauges which let me keep an eye on the pressure inside the flask. To get the correct ratio, I assumed ideal gas behavior and calculated the amount by partial pressure. Looking at the reaction, one molecule of trifluoroiodomethane reacts with one molecule of nitric oxide to form one molecule of trifluoronitrosomethane.
Wow.
So, if I fill the flask
Mix them with equal
0.5
pressures.
bar of each gas,
You'll get your
the
equal
initial pressure in the
of
flask is 1 bar.
product,
Atmospheric pressure.
and you're gonna get low
After
pressure.
the reaction, there will only be half as many gas molecules, so the pressure drops to 0.5 bar. Lower pressure also means the blue color would appear weaker than at atmospheric pressure. To avoid that, I decided to pressurize the flask to 1 bar for each gas. So the flask starts at 2 bar and ends at 1 bar after the reaction. This also allows for a larger batch. I first added 1 bar of trifluoroiodomethane and then 1 bar of nitric oxide. You can see the gas in the flask has a slight orange tint.
Funny how
That's
he's
due to
doing
the
it this
nitrogen
like this
dioxide
large of a scale. He
contamination I
didn't
mentioned
have that
earlier,
much gas to
but it
begin
won't
with.
be a
But I guess
problem.
he did put in all that.
Do you remember how I mentioned I
probably
should have
expanded
washed the
a hell of a lot.
trifluoroiodomethane? I filled the flask with 1 bar of the gas.
Okay,
when I
hold
later
on. I
weighed
need
the
to.
small gas cylinder.
What is this cooler?
Do you remember how I
And
mentioned
radioactive?
I should have
So
washed
there's
the
like radioactive
trifluoro-
substances in here. What the fuck is the organization in here? There's some kind of holders for some things, but oh, that looks so chaotic. Oh, that hurts to see as a lab safety professional. Come on. Okay.
Iodomethane.
Okay.
I filled the flask with 1
Think
bar
as a
of the
chemist,
gas.
not a lab
when
safety
I later
person.
weighed the small gas cylinder, far less mass had been lost than expected. My guess, CO2 had dissolved in the trifluoroiodomethane in the trap, and I ended up condensing it into the cylinder along with the trifluoroiodomethane. So the gas cylinder actually contained a mixture of trifluoroiodomethane and CO2, but it was too late to change that now. After filling the flask, I placed it in front of the UV reactor and tried to turn it on. But nothing happened. It turns out the reactor has a safety switch that only allows it to run if fully closed.
Time to bypass the
flask
safety
was
switch,
way too big
motherfucker.
to fit inside. What do you do in that case? You run the reaction in a vessel of appropriate size so the reactor can close properly and
And
no
that's
UV
not what
light
you're doing.
escapes.
Mm-hmm.
I then wrapped
Okay,
aluminum foil
fine,
around
fine,
the back
fine.
of the flask, hoping it would reflect some of the UV light that would otherwise just be lost. Here's what happens under UV light. The iodine splits from the
Safety disaster.
trifluoroiodomethane, forming a radical
Okay.
that can then react with
That's
nitric
a lot
oxide
more
to
simple
form
than I thought it would probably be.
trifluoronitrosomethane. At least that's the plan. While
where's the
irradiating, I
mercury?
stirred the mercury at the bottom of the flask with a magnetic stir bar to constantly expose a fresh metal surface. After about an hour, the gas in the flask
Can't be the
was
mechanism because it doesn't incorporate
orange?
mercury.
That was not what I was expecting. At that point, I was starting to get a little worried. I had only planned to stay in the lab for 1 more day, as that was the end of the week and the time I had agreed on with Professor Kraus. After a brief swirl, the orange color faded and you could almost imagine a faint greenish tint.
You
I
really
think the
put your
orange
mind to
color
it.
comes from nitrogen dioxide. How exactly it forms, I'm not entirely sure. My best guess, the NO reacts with the CO2 in the flask to produce carbon monoxide and more NO2. If anyone has a better explanation, let me know in the comments. Swirling the flask removes the orange color because the NO2 reacts with the mercury to form mercury nitrate and
Yeah, there's-
regenerates NO.
Oh, that mercury is
After
getting
another
torn
4
up in
hours,
there.
the flask was deep orange again, and the mercury was practically consumed. So much for a catalytic amount. looking at the original paper, it turns out the claim of catalytic
Get to a video of a poorly trained chemist next, maybe just throwing some stuff around. I see that at work every day. I don't need to see that at home, too.
mercury is nonsense. The paper explicitly states that the mercury captures both the released iodine and NO2 that is being
Could
formed.
be funny, though. Good
Basically,
torture. You have to
the
recommend me a
opposite
video.
of catalytic. In
Actually, wait, so what is
NO2
this?
that is being mercury captures this nonsense paper.
sorry.
It turns out the claim of catalytic mercury is nonsense. The paper explicitly states that the mercury captures both the released iodine and NO2 that is being formed.
Okay, so this entire mechanism down here is just horse shit. So, okay. It's not catalytic. Not at all. It's just stoichiometric. So you're actually going to get... So you're actually going to end up getting like HGI to maybe just HGI, as well as like maybe some like random HGNO. That's NG. Oops, HGNO2? Something like that. You get some kind of HGNO species as well. Okay.
Basically, the opposite of catalytic. Interestingly, this paper also mentions the formation of NO2. So it seems that CO2 probably isn't the reason for its formation after all. Anyway, it meant there wasn't nearly enough mercury in the flask. But how do you add mercury to a pressurized flask without losing gas? Luckily, the flask had a long neck that could be sealed on both ends, effectively forming an airlock. So I opened the neck to the outside while keeping the PTFE
Then you're gonna
valve
have to
on the
evacuate
other
it
end
as well.
closed. That way I could fill it with mercury without letting any
Yeah, that
gas
looks pretty.
escape from the
If only
flask.
mercury wasn't so goddamn
I tried
toxic.
to fill it as much as possible to keep the empty space to a minimum. Then I hooked the neck up to the schlenk line, pulled a vacuum to get rid of any leftover air, and flushed it with argon.
But you know,
I
fair enough,
repeated
there's
that
not that
3
much
times
air going to be
just
inside
be
of that
safe,
mercury.
and then quickly
Displaces
sealed
almost
the
all
neck
of it.
with a blind cap. Once it was closed off to the outside, I opened the PTFE valve and let the mercury flow into the flask. With fresh mercury
I'm almost certain you could probably do this reaction without mercury, because you basically just need something metal to absorb the iodine and absorb the nitric oxide excesses, and most metals will do that. I guess the only question is like, okay, the only thing to work out is like, are the metals going to be reactive with the F3C, with the trifluoronitrosomethane that you want to isolate? And, you know, mercury is a liquid, so it has that nice ability to just stir it around and expose new fresh mercury to react with. But, you know, metal powders is probably fine. That'll probably work out well enough.
I left the flask
Less toxic,
under UV
maybe,
light
you know?
overnight. All I could do now was wait, hoping the gas would finally
light
turn
show.
blue. Before we check on the flask the
Oh,
next morning,
bro.
I first want
Okay.
to introduce you to the sponsor of today's
Oh, okay,
video.
no, brother. I thought it was going to be like Raycon.
Radiacode is a portable radiation detector, but it's not just a simple Geiger counter.
That could at least be useful for somebody who actually wants to do science. At least it's not a fucking just simple ass sponsor, so. Alright, so hold on. This is.
The round bottom
in getting a Radiacode.
It's the morning
There we
of my
go.
last day in the lab. The round bottom flask has been under the UV lamp for the whole night, and I'm very excited to see whether or not it turned blue. I basically have no more time left to repeat the synthesis, so
Here goes. The moment
let's
of
hope
truth.
The flask is blue, or the gas inside the flask is blue.
I don't know why. Ah.
Uh-oh. The UV light turned off overnight. That's not good.
Well, that's disappointing.
It's almost like you
As it
shouldn't try to
turned
bypass
out,
the safety
tape on
control.
The UV reactor switch had come loose and the lamp had gone out overnight. The flask had taken on a deep orange color,
Very
and
unfortunate.
the mercury was once again almost completely consumed. After swirling the flask for a while, the gas took on a slightly
Should've used a
greenish
smaller
tint.
flask.
That was already promising. After all, orange and blue together make green. Because the mercury was almost completely used up again, I refilled it using the same method as the day before.
Yay,
By
more
now,
mercury!
The flask held
More
over
mercury!
a kilogram of mercury. I really hoped I wouldn't have to refill it yet again. But one thing was clear. It was Friday and I wasn't going to suddenly get pure trifluoronitrosomethane in a single day. So I asked Björn and Professor Kraus if it would be okay to extend my stay a bit so I could at least attempt to finish the synthesis successfully. And they actually agreed. At that point, I want to give a huge thank you to Professor Kraus and Björn. It's by no means a given.
He's not a terrible chemist. But it is, maybe, you know, just the idea of like, well, maybe think of the practical solution of like, maybe you should use a small flask that fits in the damn thing and doesn't bypass the fucking safety reactor. Maybe accept that you might have a smaller amount of product. You know, maybe, you know, read the damn literature. These aren't necessarily hallmarks. They're hallmarks of a typical chemist, but I also, like, you know, there's nothing to piss you off more than knowing stuff about the field where it's just like, man, I wish I wish the standards and practices in the field were a little bit better. Maybe the other people could just, you know, sharpen up a little bit.
That they would let me follow a project
they
for
also
so
then just be
long
like,
without gaining
I won't need to read the
anything for
literature. I'm good
themselves.
enough. Like, that's not a
big
good
thanks also goes to Daniel for letting me use his fume hood and to everyone in the beryllium lab for letting me borrow their beautiful glassware. Once it was clear that I had more time than originally planned, I decided to set
RGB
up
in
a
the fucking
second
hood all of a
flask.
sudden?
This
Happening?
time only 2 liters.
Somebody gaming?
I still worried that the reaction in the first flask might not work properly because of the large amount of CO2. This time I added a generous amount of mercury right from the start, since this
enough to
flask
poison a
offered
whole
no
lake.
way to refill it later. Both flasks were then irradiated over the weekend.
Yeah, just widen up the UV chamber even more, why don't you? An E1 reaction? Yeah, of course I
When
have
I
for
came back 2 days later,
undergrad at some
this
point.
is what I saw.
Maybe even my undergrad research. Wasn't part of my grad research.
The
but
gas in both flasks had actually turned blue.
Ah.
It looked really beautiful.
Ooh.
With the reddish deposits
Get
of
that.
mercury iodide, it even looked a bit like a planet.
That's cool.
At that moment,
That's
I was
successful.
incredibly relieved. A whole week's worth of work hadn't been for nothing, and it
See, he's a
finally
great
felt
chemist.
like
He just
I
has a
was getting close.
He's a great chemist. He just, you know, does the thing that I do in video games and probably also do in chemistry, where the most important barriers in front of you are the ones you set up yourself.
To the goal. But
Thank you.
was
Come
it
on, enough with the
truly
trash
as
talk.
blue as it could be? Or were impurities in the gas preventing it from reaching its full blue intensity? It was far from the fake picture on Wikipedia, and all the publications describe it as a deep blue gas.
Well,
There
it's
was
not
only one
concentrated.
way to find out.
Pressurize
I had
it,
to
pressurize
purify
it.
the gas.
And purify it.
I assumed that the flask mostly contained unreacted nitric oxide and trifluoroiodomethane. My plan was to separate them based on their boiling points. To make things easier, I decided to first oxidize all the
Interesting
remaining
method.
nitric oxide
But I guess it's a good idea considering you may not know what the reactivity profile of the nitrosomethane is. So you don't trifluoronitrosomethane, so that way you don't want to accidentally react something with that when like maybe a base could scrub out the nitric oxide. So okay.
to nitrogen dioxide. That way, I would end up with 3 gases that all have very different boiling points. Trifluoronitrosomethane, minus 87 degrees Celsius, trifluoroiodomethane, minus 23 degrees Celsius, and nitrogen dioxide, 21 degrees Celsius. This meant that by cooling the gas mixture to around minus 25 degrees Celsius, only the desired product, trifluoronitrosomethane, would be gaseous.
Hell, you could probably just
while
use
the
dry
other
ice and
gases
acetone again,
would
too.
stay condensed.
CF3NO
To
should be
oxidize the nitric oxide,
still
my
above
plan
that.
was to feed in oxygen from an oxyacetylene torch. To do that, I first cooled the flask in liquid nitrogen to create a slight vacuum. Then Björn helped me by letting oxygen flow into the neck of the flask while I briefly opened it. When I introduced the oxygen, there was hardly any color change, indicating that almost all of the nitric oxide had been consumed.
Promising.
Next, I connected the round bottom flask to a Schlenk tube into which I would condense all the gas. I cooled the tube with liquid nitrogen and opened the large flask. You could immediately see a blue solid forming. This was the precious blue gas I was after.
Nice.
But by the differently colored solids in the tube, it was also clear that this wasn't the only gas condensing. The plan was to first separate the gases by their boiling points and then wash the blue gas with a 4% sodium hydroxide solution. I poured this solution into a 2-liter flask and then connected it to the tube containing the frozen crude gas.
One time you moved benches to a new bench. When you started cleaning it up, you found a canister of pressurized gas under your new bench with the compound DEAD. Oh, that's fun. Yeah, dead. That's diethyl dicarboxylate, right? Diethylene azodicarboxylate? Yeah, that's mild explosive as well. The newer label should say it's mildly explosive. So that's a wonderful bench with tons of hazardous materials underneath it.
Next, I gently warmed the Schlenk tube to minus 25 degrees Celsius by placing it into a bath of pre-cooled isopropanol.
Very good
This
stewards
way,
for
only
before.
the blue gas should evaporate, while all other higher boiling point impurities would stay behind. And after a short while, you could see the flask starting to fill with the blue gas. In the Schlenk tube remained a yellowish liquid, presumably condensed trifluoroiodomethane. I discarded this portion completely and cleaned the Schlenk tube. So this single step already increased the gas purity significantly. To further clean it, I swirled the flask so that any impurities would dissolve in the sodium hydroxide solution. Before I could condense the blue gas back into the first,
Yeah, they
now
tried to
clean
kill you,
Schlenk tube,
definitely.
I first had to freeze the water inside.
Everything,
Otherwise, I would have also condensed a significant amount of water into the smaller flask. Once all the water was frozen, I cooled the Schlenk tube with liquid nitrogen and opened the large flask. You could see that the condensing blue gas already looked much cleaner than before. After all the gas had
no
been
gloves.
transferred
Yeah,
back
what do you think
into
was
the
gonna
Schlenk
happen?
tube, I kept cooling it with liquid nitrogen and applied a vacuum for an extended period to remove all low boiling gases like argon, oxygen, and nitrogen. In the 2-liter flask, a faint blue shimmer remained. This was the perfect opportunity to test what the blue gas smells like. If you're doing a synthesis like that,
I mean, sure, for the sake of science and having it documented, fine. But also, yeah, not a great idea. It's never a good idea to try to sense your chemicals with your body.
And aren't wondering what it smells like, there's something seriously wrong with you.
Yeah, just get closer. It's totally fine. It's not like, it's gonna hurt you below your detection limit.
Es ist so leicht chlorartig, finde ich. Ja, okay. So ein bisschen, so, aber so ganz sanft. Das ist inzwischen anders, ja. Das riecht nicht mehr wie vorhin. Doch, wenn du nah mit dem Folgen, du musst richtig reingehen.
Oh, you just have to fucking boof it, yeah. Yeah, the entire lab comes around to just inhale it.
Ja, oder? Aha, Tritulamin halt. Nur halt viel, viel sanfter. Und jetzt sterben wir alle.
Almost everyone who smelled the flask said it had a fishy odor, almost like an amine.
Okay.
Some also said it had a note
I know you're
reminiscent
joking.
of chlorine. Whether this is
I'm not
truly
sure
the
everyone
smell
else
of the
does.
blue gas is unclear. Of course, it could also be other byproducts or decomposition products that formed. So more research is needed
smelling
to
chemicals, getting
conclusively
brain
determine
damage.
the smell of trifluoronitrosomethane.
But I suppose somebody had to know.
Apparently, times have changed and
You
smelling
not
or
need to
tasting a
ask
compound
ChatGPT
is
for
no
this.
longer considered a proper way to determine its identity.
Thanks for wasting a small
This
ocean for this
means
bit
that
in your
before we
video.
can finally see the gas in all its glory at atmospheric pressure, I still need to record an IR spectrum. To do that, I need...
Pangu, seriously though, actually, like, I know you're bantering. Maybe cool it with the banter. Not everybody is aware of the fact that you are a very bantery person. Score, she's just messing around, but like, Pangu, actually cool your jets. Like, it's kind of rude.
Need this special tube to hold the gas. The tube has diamond windows at both ends, allowing the infrared radiation to pass through the gas. To fill the cell, I connected it to the Schlenk tube, pulled a vacuum, and then slowly let the Schlenk tube thaw so that the cell fills with the gas. Once that was done, I placed the cell in the IR spectrometer and started the measurement. The IR spectrum clearly identifies the gas as trifluoronitrosomethane, but there's one extra band I can't yet assign and which points to an impurity. I'm fairly certain that multiple distillations could get rid of it, but since I was sure the impurity wouldn't affect the color, and with time running short again, I decided it wasn't worth the effort. To finally see the actual color of the gas at atmospheric pressure, I connected a 250 milliliter flask and let the frozen gas inside the Schlenk tube slowly thaw and flow into it. And here, for the first time, you can see the blue gas in all its glory. Even though it's still slightly impure, I'm fairly certain that the color wouldn't change significantly if the gas were distilled several more times to achieve complete purity. It's always described as a deep blue gas, which is, of course, a very subjective statement. But I would
still a pretty
personally
cool
call
blue
it
gas. It's
light
nice.
blue.
Light
Let
sky
me know in
blue,
the
little
comments
teal.
what
You
color
condense it,
you
I'm
would
sure you'd
describe
probably
this
get a nice
gas
dark
as.
blue.
The next logical question I asked myself was, what should I do with the
Ooh,
gas?
yippee!
It would be such a shame to just throw away the result of 2 weeks of work. But it couldn't stay in the flask either. Even well-greased joints are never completely
Make a new gas
airtight in the
cylinder,
long
store
run.
it.
For that
Someone else
reason,
can figure
I
out
had
what
the
to do with it.
university glassblower modified 2 flasks so I could seal the gas inside. To do this, I connected the modified flask to the one containing the gas and evacuated the system. Then I cooled it with liquid nitrogen and opened both sides. The trifluoronitrosomethane immediately began to freeze in the receiving flask.
Now, see, that is a deep blue and it's nice and frozen like
While
that.
the
It's
gas
ocean
was
blue.
frozen, I used an oxygen propane torch to seal the neck. In hindsight, I probably
With
should have
no
thought
gloves.
of a better way to hold it. I had to choose between
Fucking again, why no gloves? Wear cold gloves. You grab it, or like in the very least, the cold gloves will burn if you get the
freezing
fire
my
on.
fingers in liquid nitrogen or burning them on the torch. In the end though, everything went smoothly and I had perhaps created the only sample of trifluoronitrosomethane in the world. When the flask warmed up, a small puddle of a higher boiling point gas appeared.
Aw.
That's the same impurity we had already seen in the IR spectrum. In the same way as before, I also purified the gas from the 2-liter flask and condensed it into a smaller 100 milliliter one. This time I used a clothespin to hold the flask while sealing it. By the way, when Nile Red visited about a year ago, we talked about how he had planned to make the blue gas as well.
Fun
But due
overlap
to
between
other
the two of them.
projects, he never got around to do it. When I told him I had finally succeeded, he said he had no problem with me publishing my video. I hope he still makes the gas because I'm really curious to see how he would approach the synthesis, at what scale, and what his final result would look like. In the end, I had 2 flasks filled with trifluoronitrosomethane. There's probably
That
a
one's not forming
slight
a puddle at the
overpressure
bottom.
inside,
Nice.
which makes the blue color appear even more intense than it actually is. A very nice effect is to condense the gas inside the flask with liquid nitrogen and then let it slowly warm up so you can watch the flask gradually take on a blue color as the trifluoronitrosomethane evaporates.
That's so
At
cool.
this point, I want to thank all my subscribers and especially my channel members and Patreons. If you enjoy my
That's,
videos
I
and
mean,
want to support
getting into the
me,
pretty
I
colors is
would be
exactly why
really
I got into
grateful if
chemistry
you
in the
became
first
a channel
place.
member
It's why
or
almost every
Patreon.
chemist starts
You will
enjoying
find the link
chemistry
in the
when they're a
video
kid.
description. Oh, and while I was editing this video, I noticed that someone had already reported the fake photo on Wikipedia, and it has apparently been removed. So all that remains now is to upload a real photo of the gas. I really hope you enjoyed today's video. Other than that,
Yeah.
thank you a lot.
Let's check this out. Let's see. Hold on. Let me hold on. I'm gonna hide out the display for a second here. I'd like to check. Is the Wikipedia page? Wikipedia trifluoronitrosomethane. Has the picture been replaced? Wikipedia. Why is it not showing up? What? Where's the Wikipedia article for it? Oh, there it is. It's just hidden in like the AI summary or whatever. Ah, hey, look at that. Okay. Share this again. Look at that. The picture has been updated. I think it has something to do with this guy's second video. Where he follows up on this and makes it again in a different way. And look at that. Now we have an actual official picture of trifluoronitrosomethane. And you can really see that really cool blue hue in there. All right. Wow. No, this was one of the best videos I've watched in so long. I've been meaning to watch this one, but I've been kind of focusing more on like the maybe more well-known chemicals in the domain of like or the more known chemistry YouTubers for, video reach purposes. But now that it's like, well, Nile Red and Explosions of Fire haven't uploaded anything in a while, I had the great opportunity to watch this, and man, that's cool. This is one of the coolest videos I've watched in a while. This really tickled the chemistry brain. It's an obscure as hell compound, and its most important factor is that it's a blue gas. Hell yeah. So with that, I think that's a pretty good high note to leave things off on for the night. Unfortunately, we can't get to Styropyro's death machine or whatever the hell he made this time around. But that's all the time I have tonight. So thanks for joining me, sticking through, watching, all these videos and, hearing my takes on what's happening. Next week, we'll be back with, Mega Man and some Doom. Go to No Kings on Saturday if you can, because, hey, that's a good thing to be supporting right about now. I know I sure as hell am going to go to mine. Be sure to like the video, hype it, share it with your favorite chemists, besides me, of course. And do all the other analytical stuff to help the channel grow and make me happy, because that's what you want to do for me. Please, please, I beg of you, please. Yeah, I'll see y'all next week. Good night, everybody.